Um, if there's one thing that irritates the crap out of me, it's these posts that are popping up in various groups that bash 3D printed fuselages without any real experience. They're not based on flight tests, not based on actual crashes. They just seem to be vague assumptions and recycled hearsay. Let's be clear. 3D printed fuselages aren't perfect, but neither is foam, fiberglass, or every material has its trade-offs. What matters is how you design, print, and fly. Most hobby-grade fuselages are printed using either PLA+, PETG, or ABS. These aren't just plastic toys, they're thermoplastics used in automotive parts, medical devices, and industrial tooling. PLA Plus offers a tensile strength of around 60 megapascals. PETG even higher, with better impact resistance and thermal stability. ABS is tough and widely used in commercial grade applications. These aren't brittle shells, they're engineered components. And when printing with proper settings, they can take a surprising amount of abuse. One common concern is moisture absorption. Yes, PLA filament on the spool is hygroscopic. It absorbs moisture from the air, but once printed, it absorbs moisture much more slowly. The internal tension is gone and the material is now a solid structure. And it's not just PLA, every material, fiberglass, carbon fiber, even aluminium, interacts with moisture. The difference lies in how much they absorb and how it affects performance. Moisture is a universal engineering challenge, not a 3D printing flaw. The real issue isn't the material, it's the print quality. Poor layer adhesion, low infill, or rushed slicing can compromise the strength. But that's not a 3D printing flaw, that's a user error. Experienced builders know how to tune their slicer settings for optimal layer bonding, reinforce stress points with ribs or thicker walls, and use post-processing like annealing or epoxy coating for added strength. It's not magic, it's just method. Right, let's talk results. Across the Flywing community, builders have successfully flown 3D printed fuselages tailored for models like the FW450 and the Bell electronics. These designs often include functional airflow vents to cool the AC and battery during flight, combining scale realism with practical engineering. Some pilots opt for military-inspired shells, others for sleek civilian profiles. What matters is that these fuselages have been flown in windy conditions at high speed and even survived mild crashes. When printed and mounted correctly, they hold up. And when they don't, they're repairable. You can reprint a damaged section for a few bucks. Try doing that with a fiberglass shell. So, let's put all this into perspective. Foam. Great for crashes, but not exactly scale accurate or durable. Fiberglass. Strong but brittle, and expensive to repair. Carbon fiber, excellent, but overkill for most hobbyists and not easy to customize. 3D printing offers a middle ground, customizable, affordable, and surprisingly strong when done right. Let's actually bust a few myths while we're at it. Number 1, they shatter on impact. Well, okay, only if printed poorly. With proper infill and wall thickness, they flex and absorb energy. But yes, they do break when they crash, but that also transfers some of the forces away from the electronics. So isn't that basically a good thing? Myth number 2, they're too heavy. Well, that's not really true. With smart design, you can match or even beat the weight of some fiberglass shells. Myth number 3, they're not professional. Well, tell that to aerospace engineers prototyping drone frames with the same materials. Myth number 4, they explode mid-air. Well, that's a joke, isn't it? This is just pure fiction. There's no mechanism in a printed shell that causes spontaneous failure. What people are usually seeing is a mechanical failure, like a loose canopy, a broken mount, or a battery ejection, none of which are exclusive to 3D printed parts. If your fuselage disintegrates mid-air, it's almost always due to poor mounting, bad print settings, or neglect, not because the material is inherently unstable. And let's be honest, if your Heli explodes mid-air, the fuselage is probably the least of your problems. So, the next time you hear someone say 3D printed fuselages are dangerous or a waste of time, ask them this. Compared to what? If you're still skeptical, that's okay, but don't dismiss the entire method based on assumption. Try one, fly it, crash it, learn from it, and then decide. 3D printing isn't a gimmick, it's a tool. Like any tool, its value depends on how you use it. In the right hands, it opens up a world of possibilities for RC pilots who care about performance, customization, and creativity. This kind of blanket rejection is rooted in old-fashioned thinking, where people are living under a rock or don't want to try new things, where anything unfamiliar is labeled unsafe and innovation is treated with suspicion. But the hobby has evolved. Materials have evolved. Techniques have evolved. It's time the mindset did too. Let's move past the myths and focus on what really matters. Building better, flying smarter, and sharing what we learn. Guys, thanks for joining. If you like this sort of content, hit the like and subscribe, and we'll see you in the next one.